everyone, or good evening if you are tuning in from the other side of the world. I hope everyone is having a good day. And yeah, hello, morning, Roy. Yeah, so I hope you guys are doing well. We have yet another webinar today, sharing for the ISC Space Challenge series. And today we will have Ms. Ku Ling Ing from the University of Colorado, who will be sharing with you a little bit more about specifically the Van Allen belts, but also other the different missions that will be taking place, that have taken place and will be taking place regarding the Van Allen belts. So as usual, we are recording this session. So if you have registered, don't worry, we will send it to you eventually. I know we take some time with sending out the links, but we will get it out to you guys eventually. And as usual, if you have any questions, please use the Q&A box, and we will try to get through as many of them today. But yeah, otherwise, I will hand it over to Ms. Ku to kind of share a little bit more about herself and take over the presentation.
Hello, everyone. Let me share my PowerPoint. Let's see. And you should see the big screen right now.
Yes, you are good.
All right. Well, welcome in. I'm very excited to talk about the radiation belt stuff today. But before I talk about, well, I'm Ling Ying. That's my first name, or Ling Ying Ku, or that's the US way of saying it. I guess in Southeast Asia, we do Ku Ling Ying. I'm originally from Malaysia. And I came to the United States about like 8 years ago for my undergrad study, and I did my undergrad in University of Michigan, Ann Arbor, and as a mechanical engineering student. And Michigan is really, I guess, really active in the space weather and space research part. So I stumbled into it and got really interested, and eventually did my PhD in it. And actually, my PhD has been about the Van Allen probes radiation belts. I'm still working on potentially, well, actually, I schedule the defense sometimes in the December. So, well, it's coming to the end, but who knows? So yeah, that's my journey, I guess, like a very short introduction about me. And for this presentation, really, I guess I'm focusing on more of like what Julian say. I'm gonna talk about Van Allen probe radiation belt, some introduction. From what I heard, Gankai gave a really good presentation that you guys are the expert right now. So I'm not gonna delve too much into the details of the radiation belt, just give you some data, some measurements from Van Allen probes, and then we're going to talk more about the missions, since I know you guys are designing the missions. So hopefully that gives you some inspirations on what to design for. And so yes, I can, yeah. So we're going to talk about the radiation belt 101, just some very simple, high level overview about radiation belt, and then Allen probes mission, and finally we're going to talk about some missions after Van Allen probes. And I do want to make this interactive, so if you have any questions, I'm not sure if I can see the chats. I don't think I can, but if you have any questions, I guess you guys can shout out, or yeah, I guess.
No worries. If there's questions, I can shout it out for them.
Okay, perfect. That would be great. Thank you. Okay, so yes, that sounds great. So let's get started. So I guess we dial it back to 1958. I'm not sure if Gankai told you guys about this, but US launched the first satellites on 1958. That actually really opened up the space weather, space science page. And on the picture here, we have three really the key player for these missions. We have the William Pickerings, who designed, built the satellites. We have Dr. Van Allen, who designed and built the instruments, and we have Dr. Von Braun, who is the leader of the team that built the rocket. So they are really the three key players who really make this mission possible. The first satellites, make the first satellite possible and successfully launch. And at the state of understanding at that time in 1958 was outside of Earth, we have atmosphere, and outside of atmosphere, we have nothing. We have cosmic ray. So at that time, the objective is actually to, whoops, for some reason I cannot forget. Yeah. Well, the objective is to study the cosmic ray and micrometeorite. So what they have a very simple Geiger counter, which is basically just counting the cosmic ray that's hitting on it. And what happened was after launch, the Geiger counter just saturated, and they were just wasn't sure what's happened. Some people were like, is the instrument not working, But eventually, after a certain distance, the Geiger counter decreased again, go to void. And that's when they realized that maybe what they're measuring is actually just very intense charged particle radiations. And after there's some more follow-up missions, Explorer 2, 3, 4, 5, etc. And eventually they realized that we actually have two belt structure just outside of the atmosphere. We don't just have void, we actually have some intense radiation just circling around the Earth, got trapped by Earth's magnetic field. And that's actually the definitions of radiation belt, is the energetic charged particles that are trapped by Earth's magnetic field. And I assume that Dr. Poe or Gamkai already gave you guys this overview of the motions of particles. I think he did. And you guys know about the gyrations. And one really important thing about radiation belt is charged particles really influenced by the magnetic field and the electric field. So in this case, because of magnetic field, they would gyrate around the magnetic field line. The charged particle would gyrate around the magnetic field line. And because the Earth is a dipole magnetic field, so you have a dense, magnetic field gradient. So you have a stronger magnetic field near the pole side, and now equator, you have a weaker magnetic field. So the particles will bounce between the two hemispheres. At the same time, they also will drift around the magnetosphere, around the Earth. And another thing, important parameters that we use a lot in the radiation belt science is L shell. So basically is the radial distance in Earth radii at which the dipole magnetic field line crosses the magnetic equatorial plane. So at L is equal to 2, which means that it's about 2 Earth radii apart, where the dipole magnetic field line crosses the equatorial plane. So that's an important parameters, because I'm going to show data that you're going to see that over and over again. So now go back to this classic two belt structure. We have the inner belt and we have the outer belt, and they're not the same. So the outer belt is famous for being really dynamic, and they're strongly influenced by geomagnetic activity. But for the inner belt, they're much more stable, and with occasional injection from the outer belt and slowly decay, very stable, very, rarely change in terms of the dynamics, less dynamic as the outer belt. And in between that, we have a slot region, which is a low flux region that we call the slot region. And here's the data from Van Allen probe. Spoiler alert, I guess. So here on the y-axis, we have the L shell, which, like I mentioned, is the radial distance, how far away these particles are from the Earth. And L is equal to 2 Earth radii away from the Earth, approximately. So you have, so if you can guess, this will be the outer belt that you are seeing. So the y-axis is the L shell, the radial, the spatial locations or radial distance, and on the on the x-axis you have the time. So you can see that the outer belt just come in and out, and sometimes it will all of a sudden it appears, and all of a sudden it start slowly decay away, and all of a sudden it appear again. And sometimes it can penetrate really deeply and come into the inner belt, and this is the inner belt. And this we are showing it. This is the 500 keV electrons dynamics. And you see that for different energy, this is 234 keV, 100 keV, 46 keV. Different energy will have different dynamics. And the location of the slot region, the location of the outer belt, inner belt, all different for different energy particles. And as you can already tell, for lower energy, you can see the penetration happen more frequently. And as you go to higher energy, it just less frequent, and the outer belt also happen a bit further away from than the lower energy. Lower energy can penetrate much deeper as compared to the higher energy. So these are just the characteristic of the electron belt. For this talk, I'm gonna.
Sorry, we do have a question related to this part. So in case, so that we don't lose track of it later, because we find that sometimes happens. Someone asked, does the L shell include the radius of the Earth? Is it measured from the center of the Earth or from sea level?
From center of the Earth. So L shell is equal to 1 is the surface of the Earth, and then L is equal to 2 is 1 Earth radius away, if that makes sense.
Okay. Yeah. Okay.
Great. All right. No, those are good questions. And now I think I talked everything about this. Oh yeah. And for the rest of a lot of time we talk about electron belts, and most of the time when we talk about radiation belt, we talk about electron belts. But in reality, there's actually a proton belt. So here's a model, the radiation belt model. This is not actual data. Here's the electron belt. That's the one on the right is the electron belt. You can see that the very clear two belt structure, and then we have the slot region. But for proton, it's only concentrated near the inner belt. And because it only concentrated in the inner belt, it also caused problem because if we want to measure the inner belt populations, inner belt electron populations, it's very hard because the proton is, I'm going to talk about this later, the challenges of measuring the charged particle, but because of the cohabiting features that makes more contaminations when we are trying to measure electron populations in the inner belt. So now let's move gear to radiation belt missions. So a lot of time, like a lot of the science, I guess, science discovery, all the missions or observation really can open up a new field. And just like radiation belt science, a lot of these missions really bring some really cool observations that allow us to really just study and really understand more about these features. And this is just a list that was really nicely compiled. I really like this figure. I actually give an alternative title to this talk being, all this just a photo compilations of all the figures that I love. And this is one of it. This is from AFRL. They just compile all the radiation belt related missions. I guess like not all of them are actually designed to measure radiation belt particles, but they have some capability to provide us some insights on the radiation belt. So they have some instruments on board, even though it's pretty coarse, but still can tell us something about radiation belt. And because we're going to talk a lot about the missions, so I'm just gonna zoom in, and we're going to talk about, you can see different color indicate different orbit. I'm not sure what's familiar. I guess like I'm just going to talk about different orbits so that you can have an idea, a picture in your mind to picture, when we talk about low Earth orbit, what are those, and what's the advantage and disadvantage of having those measurements. So here's Earth radiation belt. We have inner belt and outer belt, and the low Earth orbit is the satellite that's close to about 300 to 400, and sometimes here the definition is 200 to 2,000 kilometers. They are very close to the Earth. You can imagine the ISS, the International Space Station, being one of them. Those are in the low Earth orbit. They're just orbiting around the Earth. And we also have the highly eccentric orbit, which means that they have which is like Van Allen probes. They have a low, they have apogee and perigee, and the perigee are close to the Earth, and the apogee is just far away from the Earth. So they are not about like, not exactly circular, they're elliptical, and oftentimes they are really far away from the Earth so that they can measure different populations. And in Van Allen probe case, they are really close to the equatorial plane. So the Van Allen probes are really about like inclination of 10 degree or so, and that's about the inclination of the magnetic field line and the geomagnetic field line, if you can see this plot right here, because the Earth's magnetic field is actually tilted a little bit, and that angle is about 10 degree, and that's the inclinations of Van Allen probes. And the low Earth orbit is orbiting around the Earth. And you might ask, like, so if that's the case, if we're so close to the Earth, how we're gonna measure particles that are like L is equal to 2, 6, all the way up to 6. Like, how are you going to measure that since we're only orbiting about like, say, 500 kilometers? Well, the clue, I guess, like the answer to it is you can have a really high inclination measurements, and imagine the dipole magnetic field like usually converges near the pole site. So if you have a really high inclination, you can really measure different populations, different L shell measurements, even though you are just at a 500 kilometer of orbit. So that's one of the advantage of having a low Earth orbit with a very high inclination. In fact, you can see that a lot of the radiation belt study, the CubeSat, they are orbiting the low Earth orbit measurements, but they usually have a really high inclinations orbit. That's because they're trying to cover a wider L shell range. As for Van Allen probe, which they are generally trying to measure, they can go further out into the actual radial location. So they're usually closer to the edge so that they can actually measure the equatorial measurements, the particles that are closer and more stably trapped. We can talk more about those if you have any questions about it, but let's move on for now. And one mission that, a couple missions that I would highlight here, this mission specifically is called CHRIS. And I would say it's the father of Van Allen probe because the orbit itself is very similar to Van Allen probes. It's about 18 degree inclinations. It's a geostationary transfer orbit, which means that it can cover from 1.01 to 7 Earth radii. And the launch date, unfortunately, it launched about 1990, but it lost contact about 1991, possibly because of the battery failure. So we only have like a year of data. It has some really good, great measurements on it, but we just have such short lifespan that we still get some good signs out of it, but still, it's just unfortunate. Another mission that's highly relevant to radiation belt science is called the SAMPEX measurement. It's a low Earth orbit. This altitude is about 520 to 670 kilometer with a high inclinations, 82 degree. And the goal is to study the energetic particles of whether it's solar or interplanetary or magnetic spheric origin. So what's really cool about it, if you look at it, it actually launches about 1992 or 1993. And it has a really long lifespan. I think the missions is only scheduled for like a couple of years, but it over exceed the expectation. It actually end about like 2013. And Van Allen probes at that time was trying to push for that deadline. Van Allen probe launched around like 2012, late 2012. And they were like, we want to make sure we have some overlap so that we can have a low Earth orbit measurement at the same time we have the big equatorial measurements provided by Van Allen probes. And they eventually did. So that was, and because of the longevity of the SAMPEX measurements, SAMPEX mission, we are able to study the really nice solar cycle variations of the MeV electrons in their inner belt. Here's the 2 to 6 MeV measurements for SAMPEX. Here again is the L shell, and here's the time. You can see that, and the black line is the sunspot number, and the red line is simply the solar wind speed. And if you look carefully, the fast solar wind speed, the higher the wind speed are, the lower or the deeper the MeV electrons can reach. Another thing is they also find that since the sunspot number corresponds to the solar cycle, they also found that the solar minimum, which is right here, actually correspond to a much weaker outer belt as well. So they found that there's actually a strong correlations as a really solar cycle variations of the MEV electron dynamics in the outer belt with the solar activity. So this is why I guess like among many other things, motivated to propose this mission, the Van Allen probe, the very famous Van Allen probe mission now, is launched August 30th, 2012. And it was previously known as the radiation belt storm probes. So a lot of time you will see articles will say RBST, and that's what we usually use. In fact, I was told that I should not use VAP as an acronym for this. The team prefer RBST versus VAP. So just an FYI. So it was got deactivated about 2019. Sometimes October and July for RBSP A and B. It's a twin satellite, which means that both the instruments on the satellites are identical. And like I say, the inclination is about 10 degrees, and it can cover about 1 RE, 1.1 RE, all the way to 6 or 7 RE sometimes, depending on the orbit. And the goal here is to study the influence of sun to the Earth. And more specifically, they want to know how these particles get transported inward and how they get energized to MEV, and how these particles, the trapped particles, get lost in the radiation belts from getting trapped to lost. And what's the balance between these different processes? There are so many mechanisms that were proposed on how this particle get accelerated or get lost, and there are a lot of discussions. And so the goal here is to trying to identify what's the relative contribution of this, and how do we understand how this radiation belt changes or the dynamic of it in the context of geomagnetic storms, so that we can eventually have a better predictions. And so the next part, I'm going to talk about the instruments on Van Allen probe, so they can have some idea of what are the measurements needed for us to have a better understanding to address all these questions. One, of course, we want to have a direct measurements of the charged particles. Here we have the suite of energetic particle compositions and thermal plasma suite, the ECT, and there are three major instruments. One is HOPE. It measures EV to 50 keV electrons. And we also have the MyGuys, which cover 30 keV all the way to 2.5 MeV or so, and REP 2 to 10 MeV. And you will notice that there are some overlap between these instruments, so that they can make some cross calibrations, and so that eventually, in fact, I think there are just some scientists have been working on to just combine all these three measurements together, instruments together, measurement from these three instruments together, so that we can have just a compilations of all these measurements. And I think they just published that not too long ago about this. And other than the direct measurements of the particles, we also have the wave measurements. One thing that I did not mention is there are waves in space and in plasma specifically. And how this wave actually interact with the particles is a question, is an active research area. So we of course have the measurements of the electric and magnetic field waves, and also the DC magnetic wave, magnetic field. And we also have the EFW, which is the boom that you see here. This is called the spin boom, and they're going to measure the electric field. We have two locations, and the delta V will give you the electric field. So they're trying to measure the electric field in the institute electric field measurements. And we also have the RB SPICE, which will provide the measurements of energetic ions covering tens of keV to hundreds of keV ions. And at the same time, we also have RPS, which give you the measurements of relativistic proton at 50 MeV all the way to 2 GeV protons. And yeah, for more details, I really encourage you guys to visit this link. Is it's a website put out by APL. Folks in APL is a really nice compilation. They have all the science highlight and all the details of it, all these instruments and all the science. So highly recommend you guys to check out this site. I think it's a really good resource. And finally, let's talk about the discovery that made possible by Van Allen probes. And of course, the first one is the tree belt structure. I guess like if you do some research about Van Allen probes, one of the first thing that comes up is the tree belt structure. This is totally unexpected. Here's actually the paper that first revealed this feature by Baker et al. 2013 on the science on science, and they actually have a. So when we first launched, if you look at the date, it's 2012, August 31st. So when it got launched, they turned on the satellites and they start receiving measurements because they want to, that's closer to the end of the SEMPAC's lifespan. So they're really trying to push for like turning it on as fast as they can. And this is when they turn it on, they were like, okay, everything makes sense. We have the typical two belt, and all of a sudden we start seeing an extra belt forming. At first, people were again like questioning, blaming the instrument again, questioning like, oh, is there any problem with the instruments? But then they found out that this is just the new dirt belt structure. So if you can see here, so this is the classic two belt. If you can see my cursor, this is the classic two belt structure, and then you can see it start decaying. As it start decaying, there's this outer belt that start forming. This is what we call the dirt belt. And this decaying belt, which is what we call the remnant belt or the storage ring. And hence you have this outer belt, the new outer belt, and then a slot region like minima. And we have storage ring, and then just our classic storage ring and inner belt again. So this is a new discovery that made possible. Really, a lot of us are surprised by this, but of course now a lot more study have been done. But still, there are more to be done. And among all of them, another discovery is, if you, I guess at this point you're familiar with this plot. We have the L shell again, and we have the time. And this is different energy. And if you go to much higher, you can see at 2.6 MeV, we really don't have many MeV electrons in the inner belt. So some talk about impenetrable barrier. Is there a barrier that's stopping this energetic particles coming in? But at the same time, we also know that SEMPACs actually show some really nice measurement that really provide strong evidence that they are inner belt of 2 MeV inside the inner belt. So these are definitely more question that was brought by Van Allen probe, I guess. So these are still some active topic area that people are still trying to figure out. So at this part, yeah. So now I'm going to switch gear to the future missions. So this is just, again, this, I think I just showed it before. We have the radiation belt. And I really just want to highlight that, oh, other than Van Allen probe, there's also ARASE, which is a Japan missions. Very similar to Van Allen probes, we call it the sister missions. They also have a very high inclination, higher inclinations than Van Allen probe actually, so that they are studying different population as well. But there's also highly elliptical, so that they can really reach really high L populations. And now really, I would say after Van Allen probes, now we actually have a handful of CubeSat missions that's lining up and trying to continue the legacy of Van Allen probes. And when we talk about CubeSat, I cannot but have to talk about the Colorado Student Space Weather Experiment, the CSSWE. In fact, some people even claim that this is like the most successful CubeSat missions. Its goal, again, is to trying to study space weather, specifically radiation belt. It's a 3U CubeSat, so it's like a loaf of your bread. It's a bread loaf, and it only has one instrument, which is called a reptile. And if you follow this presentation really closely, you'll realize that the rept is the same as the instruments that was on board on Van Allen probe that's measuring 2 MeV to 10 MeV electrons. And indeed, reptile is like the mini versions of rept, hence the name integrated little experiment. The structure and the design is very similar. In fact, they are built about the same time as rept. By the same team as well. And here's just a comparisons of the reptile measurements with my guys, because reptile actually measure much lower energy than rept. They're measuring 580 kV all the way to, I would say 3.8 is probably, and there's some integral channel as well, but they only have 3 channels on there. And you can see if you compare the reptile measurements with my guy's measurements, which is also the instruments on Van Allen probes, you see that they actually match pretty well. My guy's is again measuring the steadily trapped population that's closer to the Earth magnetic equator, while the reptile is measuring the low Earth orbit, the particles that have been drifting and bouncing, and sometimes some of them are probably precipitating into the atmosphere. So they're measuring different population, but in terms of the dynamics, very similar, which draw the confidence to our measurement as well. And in fact, because we know so well about the CubeSat itself, we are able to solve some really, the title being the major space mystery. I don't want to delve into it because I want to save time for the other CubeSat missions. But because we know the instrument so well that we are able to really identify some features that people just disregard or just regard it as contaminations, and eventually we lead to this discovery that lead to Nature publications actually. So this is the follow-up missions, CIRBE, a Colorado Inner Radiation Bioexperiment. This is the CubeSat that I've been working on really since the beginning. And this is a 3U CubeSat at low Earth orbit. And the orbit itself, it has not launched yet. In fact, it got pushed back. So it's already got selected, but because of the rocket issue, they got pushed back no earlier than 2023. And the orbit, the ideal orbit will be 500 kilometers with the inclinations. Of course, the higher the better. So we are just proposing that anything greater than 65 degrees, okay, but of course 98 will be perfect. And the goal here is, instead of just having 3 channels, we want to, now we see the potential of reptile. We want to push the limit. So we want to measure not just 3 channels, but much finer than 3. And of course, we know that there's there's proton contamination in the inner belt. So we want to make sure we really can minimize the background contaminations. And how we do that, here I'm going to talk about the challenges of measuring the energetic particle in space. So here's this is actually the actual instruments cut of just a cut of what the instrument looks like. And I'm shooting particles. This is just a simulation that I've done. And I'm shooting particles, different energy and particle types. So this here is the 300 keV electrons, 1.5, 3.5 MeV, 10 MeV electrons. As the white line is what the actual simulated particles, and the green light is just the secondary products. Could be gamma ray and could be some secondary electrons that's generated in the process. As you can see, if you go up to like really high energy, even though they don't penetrate physically, hard to penetrate in, but you can see that the secondary products increases as well. And even worse for proton. For proton, for lower energy, that's still fine. But if you go up to like 100 MeV, the shielding whatsoever, it just doesn't matter to them. They just can come straight in and just disregard the fact that there's actually shielding. They just don't see it. And because they move so fast, they can deposit so little energy that we will think that is actually electron. So it's important for us to identify which are proton, which are electron. And to do that, here's again the cut of the instruments. We have the beryllium window. Oh, actually, I did not talk about this. I think it'll be interesting. So the way we're measuring it is we have an opening. So the electrons are welcome to come in anytime, but at the same time, we have the beryllium window which is blocking them. The beryllium window will block out anything lower than the particles lower than certain energy will not be able to come in. With this thickness, we can block out anything lower than 250 keV or so electrons. So those electrons will not able to come in, but higher than that, they can start penetrating through and deposit energy on the 4 detector that's behind the beryllium window. We have 4 detector, and the detector, we divide them into the inner ring and outer ring. The inner ring is the active area, and the outer ring is what we call the guard ring. So anything that trigger the guard ring, we will say those are most likely coming from passing through the shielding. Those are probably coming from proton. We want to get rid of them. And using a more advanced electronic anisologic equation, we are able to go from 3 channels to 60 electron channels. And here's just one of the example, again, the simulation run that I've done. I've shoot the particles, and you can see that this is just all the particles you will measure on the 3rd and the 4th detector. And once I trigger on the guard ring, so I say anything that trigger the guard ring, I want to toss them away. I don't want those measurements. You can see that I start seeing a very, very interesting patterns start showing up. And then I say, okay, well, not just the guard ring. I want to make sure the particles coming from the opening. They're coming from the door that I open for them, not from other way. So I want to make sure they trigger the first detector as well. So D1 must be triggered, but not the guard ring. So once I did that, I get rid of particles that can coming from the back, but did not make it to the D1, the first detector. And finally, we can really divide all this population into the particles that, based on the pattern they exhibit, we can actually tell that, okay, this population, for example, the red are the particles that stop all the way in the 4 detector. And the coming from the green, those are the particles that can penetrate all the way through because they are moving so fast, they actually deposit less energy than the range proton, which is the particles that stop in the detector and deposit all that energy in the detector. So we can separate them into different populations, and then we can further bin them into different channels. And here's the channels that I've been slicing them up. So once we divide them into different population, range electron, penetrating electron, range proton, penetrating proton, we divide them into different channels based on the total energy they deposit. So here we, so for my guys, we have 3 electron channels. Now we really have 60 electron channels. For range electron, we have 50 channels. You can see each curve represents each channel and what's the incident energy that each channel is measuring, or the effectiveness of each channel at measuring certain energy. And you can see that we can have a really well-resolved measurements for each channels. So we are really excited for this to launch so that it can provide us a really fine energy resolutions measurements. And the next part is the mini RBST or Van Allen probe, which is the GTO set. In fact, this is the first for the CubeSat missions to go geotransfer, to go to the geosynchronous transfer orbit. They're shooting for an inclination 0 to 51 degree. I think the launch date, they're still trying to get one, potentially launch in 2022, 2023. Still a question mark, but eventually they're also trying to study so ideally, all this CubeSat will launch about the same time, and then we're able to, for example, the Survey will be able to measure the inner belt populations, while the GTO set will provide us the outer belt measurements as well, so that we have some coordinate efforts that's ongoing right now to hopefully, we're CubeSat, so we're piggybacking on the big missions or the launches. So it's hard to coordinate, but there's an attempt on that. On the GTO set, there are two satellites on, there are two instruments on it. One is the mini MiGuys. So on Serbi, we have the mini rep. On GTO set, we have the mini MiGuys that's measuring 200 keV to 2 MeV electrons, very similar range that we're measuring. But they have much coarser energy channels. They have 10 differential energy channels. And at the same time, they also have the magnetometer boom. There's measuring the magnetic field as well. And finally, I think I'm just hitting on time because I want to leave more for questions. So here's the Apex. This, I think, is a very cool missions that I just put in actually last minute. It's launched potentially there's actually a question mark behind it. 2022, 2023 is still, I think they just got selected for a launch, but the launch hasn't been manifest yet, meaning they have not announced the actual launch date yet. So what they do is very cool, I think. What they're trying to measure, again, they're trying to measure the particle measurements. There are going to be a low Earth orbit. It's a 6U CubeSat. It's a low Earth orbit again, and hopefully in a high inclinations. And they have the particle measurements that's just looking up and trying to measure the particles they're precipitating. And because when the particles, when they precipitate, interact with the atmosphere, they actually release an X-ray that's shown in the yellow line here. And they also have an X-ray that's trying to capture that. So they will have an X-ray that's looking down and trying to capture the precipitation signal. So they can make a comparison between the X-ray. And X-ray, I think this is a rather new measurements to capture the energetic particle signals. So they're trying to verify if the X-ray and the particle measurements will be consistent. So this is also a very exciting missions that's coming up. In fact, there are a lot more. I know there's like 2 or 3 more that's coming up about radiation belt and trying to study radiation belt using CubeSat. So really, after Van Allen probes, it looks like the CubeSat era just begins. A lot more CubeSat, radiation belt related CubeSat mission has been selected and will be launched soon. So I think this is just a perfect timing, I guess, for you guys to design one. Well, I guess that's the end. Well, I have a reference here in case you are interested, and also fact check all the stuff that I say. And finally, these are the mission that I've been talking about. With that, I will open up for questions.
So feel free to submit your questions, anybody, to the Q&A box, but we do have a couple already in from Yong. He asks, from the data from the RBSPs and the POESs, can we assume that a gentle plasma gradient for the inner or outer belt or both? Should I rephrase that? Should I read that again? From the data that you shared regarding the RBSPs and the POES,
right?
can we assume that I think there is a gentle plasma gradient for the inner belt or the outer belt or both?
We don't really, a plasma gradient. It's an interesting way to phrase it because we don't really talk about gradient. I guess we do in the sense where,
I'm not difficult questions.
Yeah, I guess like, can you elaborate a little bit in terms of like, are you trying to ask?
Maybe Yong, if you are able to elaborate on the question a little bit, either in chat or post another one in the Q&A, feel free to do so. I actually have a question. So I know in the previous sessions, we kind of talked a little bit about how durable certain satellites are, and I think it was kind of established that maybe CubeSats can tend to be a bit more vulnerable to the radiation belts just because they're so small and there isn't a lot of leeway on how much you can build around it to protect it from radiation belts. But then looking at your presentation, we see that a lot of the upcoming ones are CubeSat missions or smaller satellite missions.
Right.
And then is there a reason that you think that maybe that seems to be the direction that people are going in, even though they are, of course, a lot more vulnerable? And then I'm guessing that the mission times are generally shorter.
Yep. Yeah, the mission time, I guess, like from the planning all the way to execute or launch usually shorter, but like what Sempex has shown, like small, like Sempex is not actually that small, but a lot of the time the lifespan of a CubeSat really depends on the orbit. So the higher you go, it actually better just because you have less atmospheric drag. And a lot of time there's no fuel on the satellite, unlike the ISS. Just like ISS, that from time to time they have to have the fuel to pump them up, to have a boost. And because we don't have that capability, so if you have a low Earth orbit, a lot of time the limitation really is because of the orbit itself. So that's, but in terms of I don't think I have a low Earth orbit measurements. You are not actually constantly, because we are at such a low orbit, you only see enhancements or strong radiations at the SAA region because the Earth is tilted. So there's a region where the magnetic field line actually is weaker. So the electrons that are bouncing around, they actually can go deeper into the altitude. And because of that, that region has a stronger flux or intensity. But otherwise, you are really measuring you are not really seeing much because you are at such low L and you're protected by the Earth magnetic field. The particles cannot really come in that low. So you are, for the most part, you are safe from that. So really the limitation of the lifespan, and a lot of time, I know a lot of CubeSat what have done is once they go into the SAA region, which is the region with a weak magnetic field line, weak magnetic field, and hence the particles, a stronger intensity of the flux, those regions they'll just turn off the CubeSat or the instruments so that it will protect them from all the single event upset, which is the particles just hitting on the electronic and just flip the switch in a wrong way. So they'll just turn the instrument off so that they can protect them from all this radiation. But other than that, really, it's a pretty, I wouldn't say super safe, but also not as dangerous as people think.
Okay. Which kind of like leads to the next question. Someone asked that, are the CubeSat satellites that you kind of shared designed to protect itself from the intense radiation in the radiation belt, seeing as they are sent specifically to study?
I guess yes and no, because we are meant to measure them, right? So we have some shielding to remove the particles that we don't want to see. For example, the background proton contamination that I've been seeing, I'm talking about, but they are built so that they can handle the, like, worst come worst, it just gets saturated. But it's, and even though we talk about, I show you all the red curve, red plots, but honestly the flux that we're talking about, the density wise, is actually rather low. It's about 10 to negative 6 cubic centimeters. So it's a very low in terms of like our atmosphere. Compared to our atmosphere, this intensity is really low. So it only happened like once in, not once in a while, but less frequent than you think. So the saturation that happens, or the shielding itself is actually enough.
We do have a follow-up explanation from Yong. I think he was saying, so the thing about he asked is a gentle change of phase space density over different L shells, a more appropriate way for phrasing it. Maybe I think that's what you're talking about.
Got it. Yeah. So yes. Here I was trying not to show this plot because I was trying to make it in a simple language, but since you asked it, so the phase-space density, for those people who are not familiar with it, is basically, remember the gyrations, the bounce, and the drifting, we can convert it to a dimensions where all this, we are assuming that so long as this gyrations or the changes in the magnetic field or changes in whatever that happens within a time scale that's much shorter than the gyration. Gyration is really fast, like within like milliseconds, no, millihertz. Yeah, millihertz. So it's really fast, really, oh, sorry, kilohertz. So it's really fast. So those particles, as long as the changes that happen within that, less than that, or longer than that period, then we are fine. So we can convert it to a dimension where the phase-space density, and this is what he was I think he was referring to. And in fact, one of the discovery, I guess, in the Van Allen region is, before that we thought that a lot of the time the source of the radiation belt is of the particles is actually outside at a higher L, and then they slowly, because of the density gradients, the phase-space density gradient, we have a higher populations coming in from the outside, and they, without going into much detail, from a higher L, and then they will slowly radially diffuse inward. That's what they thought as the main mechanisms. And what Van Allen shows that there's actually a strong evidence that show that there's a local acceleration that happened inside. So the gradient is not really that gentle change of gradient. I guess you're referring to more of the radial diffusion, something that's more gentle change. But with Van Allen probe, we are actually seeing more of a local acceleration. There's just some local acceleration that happens at the heart of the radiation belts, and we think that that's because of the wave and the particle interactions. There are some wave that happens at the heart of the radiation belt, and that interact with the charged particles, and that will cause the accelerations at the heart of the radiation belts. Yes.
Another person asked, could you elaborate a little bit more on that impenetrable barrier that you were sharing about previously?
Yes. Yeah, so there's a lot of talk. Let me see if I can find the figure. So one of the discovery, I guess, was, like I say, there's not much few MEV electrons inside the inner belt, and seems like the MEV electrons all will not reach further than 2.8. L is equal to 2.8. It seems to be higher than that. You can see, like, for example, L3 is here, and it's just slightly inside L3. And it seems like within the Van Allen probe area, we don't see a big enhancement that happened much lower than that. In fact, my group have been looking at this, and it's possible that you penetrate the impenetrable barriers. Really, the impenetrable barrier is, we think that is because, actually, well, now that people have been, there's different voices. Some of the voices have been saying that because during the Van Allen probe area, we are actually at a very quiet solar cycle. If you look at the solar cycle, this is the solar cycle. You can see that this is the Van Allen probe area. We are at a really, really low, really weak solar cycle era. And we think that because of that, we don't see as a big storm as what Santex has seen in like 1993 or something. And because of that, it's appeared that there's an impenetrable barrier because the sun is just not as active as before. So so we just not have as strong of an activity as what we had before, and hence it seems like all the enhancement that we see are still pretty far away what we thought it could have reached, or what we've seen before. So that's what the impenetrable barrier that people were talking about.
So some people are asking also if you are able to provide sources for collecting all these data from the Van Allen probes. Are they open source? Are they somewhere online that they can use for reference?
That's a good question. Oh, well, that's one nice thing about Van Allen's or NASA missions really is they're all open source. You can go to if I type in I guess I can type the answer, I guess. There's a website called the CETA web. It has all the missions that a lot of them that are listed here, they have the measurements in there, and then you can find, and it's all publicly available.
Is it CDA web?
Oh, CDA web, yes.
Okay, hold it. I think I found the website. I will share it in the chat for you guys so everyone can access it as well.
That would be great. Yeah, if not, I can also send it to you. You can share it with them.
So Carl asked, can you tell us a little bit more about what it's like to be in a CubeSat project? How does it start? What are the kinds of people that you work with in the team? And how long does the process typically take, I guess?
Right. Yeah, so I work in this project, this mission specifically about starting 2018 or so. So 2018 is when we actually proposed it, and then we got selected, and we have been working on it since. So it's about 2 to 3 years, and now we are actually finishing up all the calibrations. The plan is to the flight, everything is integrated. We're just going to run more testing and eventually put in the storage at the end of the year. So, well, for me, my role is the so-called instrument scientist. So I've been working in terms of deciding what's the energy resolution that we want, what type of energy range that we want to cover and stuff like that, run the simulation, make sure the instrument that we're going to build will be able to address all the science questions. So really how it started, I would say it started with a science question. We will propose that, or in this case, we're trying to study the inner radiation belts. So we propose that, and we say that, okay, now we have this old missions, this instrument that worked just incredibly. We're trying to push the limit. And by doing this, we're able to do what? So usually you start with a science question, and then we address how we're gonna tackle them. And that's how it started usually. And then of course you're going to have, in our case, we have some really experienced project manager who has been working with a lot of space mission. So he's just been like, he's almost like a system engineer who we oversee all the engineers, all the mechanical engineer, electrical engineer. And these are the people that I work with, the electrical engineers most of the time, because we have a microprocessor. We will have to tell them, oh, this is the logic equation that we want to use on the microprocessor. Please implement it for us and stuff like that. There's also flight software who is trying to basically all the commands, all the data that we get, the flight software will take care of it. And the flight software will pass it to the ground stations. Well, in the space, I guess, in the space, well, the flight software will have the commands, and they will send it down, and then the ground station will take care of the package, and then will send it to us so that we can analyze that. That's usually how the process goes. Is, I guess, the electronic mechanicals at the beginning, we will work very closely together to build the instruments or to design the instrument, and then we will have the flight software who say, okay, these are the comments that we want, or these are the data package that's will coming down, and they will, and then the ground station will receive the package, and then you'll give it to us. So that's usually how it goes.
For people who do not know, package isn't like a physical parcel.
Oh yeah.
We're talking about a data package, so like the data that comes down from the satellites.
Thank you for the clarification.
No, because I realize some of our students might be a bit like, if they're not in the field, it's a bit, because even when I first came in and then like joined, I was like, they were saying packages. I was like, what are they sending down?
We're just passing the parcel from one person to the other.
Yeah. But since we're talking a little bit about instrumentation, I guess there was a follow-up question on the impenetrable barrier, which is that if someone wanted to try and study this impenetrable barrier, what sort of instruments would be necessary, or instruments would be good to use in this case?
Right. Well, in this case, I guess just like what I mentioned with the survey, we want to have fine resolutions of the measurements. Like SAMPEX, it really covered 2 to 6 MeV, and I already showed that there's really energy dependent dynamics. So we want to have a really fine energy resolution so that we can see that, okay, at this energy, it can go down to this, it won't go down much lower. So you want to have the fine energy resolutions. And then of course, there's contaminations that happen. So you want to make sure you can reduce the contamination. So I would say that's like the two key that we're trying to, I think we have some clue on how to solve them, but of course, when you talk about electronics and instrumentation, there are just so many elements that can go wrong. So yeah.
Okay, our last question actually, which is nice because we are just on time. Can you comment on how the fact that we are in the weakest solar minimum will affect the ability of future CubeSat missions in achieving their science objectives?
Well, see, I get this a lot. A lot of like the senior scientists will be like, "Oh, you guys won't get the glorious big storm that we had before." But there are still some storm that happen, you know, during like the pretty weak solar cycle. It doesn't mean that we won't get any big storms. Big storms are great because it will actually induce a lot of interest, and a lot of people want to mitigate that. But at the same time, because it's quiet, we are able to study more like different stuff. For example, the inner belt, we know that the electrons come in, they will slowly decay. But one of the mystery that I did not touch about is the theoretical predictions of the decay time once it come in versus the actual observations is like orders of magnitude off. So during this quiet time, this is like the perfect time for us to study the decaying time. And one of the interests, for example, like the AFRL, which is the Air Force Group, or like LANLOL, which is the Los Alamos National Lab, who is the one who actually built the nuclear bomb. So they have been really active in like the nuclear project. One of the motivation is, say some nuclear detonations happen in somewhere, they want to measure. So if the MEV electrons reach the radiation belt, how long does it take for it to actually decay and won't affect, you know, the satellites? And all this stuff will be very helpful if we have a weak you know, if we have a weak solar cycle, which means that, you know, quiet time, and these are the perfect time for us to really study this like more quiet dynamic as well, quiet dynamic, so to speak. But yeah, so that would be my question to that. So it really depends on how you phrase. There are just still many puzzles in the radiation belt science. So there's not just the big storm, but there's also some more subtle uncertainties in the models and also the observations that we will be very helpful even with we are in the solar minimum. So
yeah, actually this is one of the questions that came up the last few times we've been running the webinars, which is that what are some of the things that are interesting to study in the Van Allen belts at the current moment? Like what are some of the mysteries of the Van Allen belts at the current moment that they can possibly study?
Yeah, no, there are a lot. This is what makes us allow us to make a living, I guess. There's still, like I say, the observation lifespan is still like orders of magnitude away. And even like we say that, okay, we have a lot of measurements, but still the predictions or the models doesn't match up with the observations. So why is that? So theoretically, there's a lot of stuff that still need to work on. I guess for more relevant stuff, yeah, I say about the energy resolutions, because, and another thing that people are trying to do is the pitch angle. So we are, especially if you are at the lost cone region, or even Van Allen, one thing that I did not mention is actually spinning. So they are not only measuring the stably trapped particles, but the particles that are actually bouncing around and stuff like that. But so there are also studies that are trying to study more in details the pitch angle, which is where the particles velocity vector with respect to the electric field. So they're trying to see what's the distributions of these populations. So those are still, I would say those are really key to understanding how this particle got dissipated or get lost in the atmosphere. So like the pitch angle, having a spinning satellites will be very helpful to understand like the distribution of particles at different magnetic field. And different magnetic vector, I guess, in essence. Oh my, it's getting late. I'm mumbling, but yeah, that's the gist of it.
Okay, Pranav asked that how do the existing probes do the mapping of the Van Allen belts around Earth?
The mapping, well, one thing is we circle around the Earth, and because of the orbit itself, right? So it actually go really far out and come inward. And what's really nice, because we have a pretty long mission durations, so it actually go around the Earth. So we actually have the entire, I think it go around the Earth, or we call it local time. So different regions of the Earth. I think for a couple times. Every 1.5 year it will circle around. So we have like a handful of mapping, but every time you have a different solar and geomagnetic conditions are different. So it just, every time you see something different. So that's what makes it interesting. Like I say, the sudden appearance of a strong enhancement, and then all of a sudden it disappears. So how is that happened? Yeah, so all this stuff are still awaiting to be answered. We have an idea, general idea, but not a very detailed one. So yeah.
I guessing the orbital mechanics of like your missions are also very crucial to what kind of data you collect. So
Right.
for everyone who's interested, we have a basics to orbital mechanics lecture next week. So that's probably if you're interested in going more into that area and like asking more questions about that and the kind of orbits that you can possibly explore for your own missions, I would advise that you could join our talk next week. I think it's a Friday night. I think we have it planned for a Friday night in Singapore time. Yeah, 8:30 p.m. GMT +8, basics to orbital mechanics next week. It'll be done by Burak, Mr. Omar Burak Iskandar, who's from NTU. But yeah. So I think the last question they have is, could the students connect with you on LinkedIn or via email if they have more questions about your research? But yeah, so feel free to reach out to Ms. Koo about any questions you have. I think we're super lucky that all our experts have been super keen to share everything that they know about. But yeah, oh, it just started raining for us over here. It just started raining for us over here. So, but yeah, I hope everyone has a good Friday evening for you and a Saturday. And yeah, have a good weekend, everybody. And I hope you enjoyed today's webinar. If we can give Miss Koo a big thank you for today's sharing. I hope you guys learned a lot.
Thank you. No, this is fun for me too.
It was super great to have you on board. But yes, but yeah, feel free to reach out to her, or if you have any questions, you can also send them to me and I can direct them to Ling Ying.
Yeah, I guess you feel free to reach, you can share my email to them if they ask for it, I guess. I'm happy to chat more offline.
Yeah. So thank you, everyone. I hope you have a good weekend, and I'll see you guys very soon, hopefully. Bye.
Bye. Second.